radiation at Rensselaer Polytechnic Institute in New York. Since 1995, he has mentored nearly 100 PhD and MS students in US and China. His research has focused on radiation dosimetry for radiation protection, medical imaging, and radiotherapy applications. He has been having continuous funding by government agencies and private sector industry. He has contributed and published 2 books, 200 peer-reviewed papers or chapters, more than 400 abstracts, and 140 invited talks. He is widely known for his work on computational phantoms and advanced Monte Carlo simulations. He has huge number of achievements to his credit, and going through that will need much more time than what we can afford today. But to just briefly mention, he is fellow of the American Nuclear Society, also of the Health Physics Society, the AAPM, the AIMBE, and also a council member of the NCRP. He is past president of the Council on Ionizing Radiation and Measurements and Standards. He has been on the editorial board of medical physics and in medicine biology for 20 years. He developed a large number of commercial software tools, including VirtualDose, Archer, DeepViewer. He has been crowned with a large number of awards. To mention some, Randal Caswell Award for Distinguished Achievement in 2015, Health Physics Society Distinguished Scientific Achievement Award of 2018, ANS Arthur Holly Compton Award in Education of 2020, ANS Rockwell Lifetime Achievement Award in Radiation Protection and Shielding 2020, and AAPM Edith Quimby Award for Lifetime Achievement in Medical Physics. With those few words, I will invite Professor George Xu to start his talk. George, the floor is yours.
Thank you, Professor Rahimi. I'd like to share the slides first because I am in Tibet at the moment. And I'd like to share with you some very happy notes before I become technical. I am in Lhasa, Tibet, which is 3,000 meters above seawater. And the video on the right lower portion is the camping. Thank you. Well, I'd like to begin by telling you my involvement with 2 companies that commercialize some of the softwares that I'll be talking about. And my presentation will follow this sequence. I will begin with anatomical modeling, which is followed by a dose reporting tool that we developed, which is followed by a segmentation tool. And finally, I will discuss a dose computing tool. So my presentation, you will see these 4 sections repeatedly. Well, everybody today realizes that we normally use 2 different methods to estimate organ doses. So on the left side of the slides, you are looking at an experimental approach, which we use a physical model or a phantom of a person or a patient. With this anthropomorphic phantoms, we can use a dosimeter, which is showing on the bottom of the slides, and we can make a measurement once the phantom is placed inside of a radiation fields. But oftentimes, we prefer a computational method, and one of the methods is called Monte Carlo simulation methods, which is what I'll be talking about mostly today. To compute radiation doses, we have to use a Monte Carlo code. We have to define an anatomical model, which is what I'll be talking about in the next several slides. In these two books and in at least one of the review articles that I was involved, we discussed in very detail about the history of computational models. Computational models actually is being widely used in radiation protection, of course, but also in medical imaging as well in radiotherapy. As a matter of fact, starting in the late 50s and early 60s, we developed what's called the first generation stylized phantoms. And then it evolved in the 1980s into what's called the second generation voxelized phantoms. And then the third generation, which is based on what's called the BRAP phantoms, which I will explain a little bit later. So with those three generations of phantoms, they coexist today, depending on your research resources, your interest, your experience. You probably have one of those computational phantoms. I think we are moving into personalization, multi-scale, from voxel to DNA type of models right now, in very near future. So let me talk about a little bit first generation stylized phantoms. This type of phantoms were developed for the needs of what's called MIRD phantoms. This is for the nuclear medicine internal dose calculations. Those phantoms came in families, as we can see from the upper left hand and also upper right hand side. Now, interestingly, those phantoms were originally first developed at Oak Ridge National Lab, but later also adapted by a German group. And those phantoms were later named Adam and Eva. Now, those names are very important when we talk about the history of computational phantoms. Based on those MIRD phantoms, pregnant patient phantoms were also developed. But less known to the research community actually are two phantoms that were developed and used by NASA. And here is showing one of the male models from that group of individuals. As I mentioned earlier, beginning in the 1980s, several research groups started developing what's called voxelized phantoms. And I'm using just my group's phantom, BIPM, as an example. But next slides, I will show many other similar and also developed a little bit earlier phantoms. But those voxelized phantoms, they look very different from the stylized phantoms I show on the previous slides. For example, those voxels are made of pixels. And in the three-dimensional manner is called voxels, or volume element. Very much like the word pixel, but this is in 3D. Now, we developed with two students of mine, Efren Chow and Amand Baskert. We used what's called visible human images, and we defined voxels by voxels. In this case, actually, those are the bone marrow. And then you pull those medical slices together, eventually you construct a voxelized phantoms. And the VIPM paper, I believe, is one of the most referenced papers on computational phantoms. As I mentioned earlier, my group wasn't the first to develop the voxelized phantoms. Actually, Peter Divino, Maria Zank, among many others that I won't have time to mention. But in this book, you will be interested in knowing which groups developed what type of voxelized phantoms. Now, voxelized phantoms were quite useful, but the third generation phantoms came very quick. So on this slide, my group developed a series of what we call pregnant patients. In this case, we defined 3 months, 9 months, 0 months, 9 months, 6 months, and 3 months pregnant individuals. And we are able to use the third generation phantoms to adjust the size and weight of the phantoms. And of course, we define obese individuals. Now, those phantoms are possible only because we use the third generation methods, which are deformable, which can be defined to as time goes on and to define motions. Now, I'd like to mention this a little bit. Well, I would say 7 years earlier, a survey paper. The paper actually discovered something quite surprising in that the number of phantoms increased exponentially. So when one of my students came to me with this data, and I couldn't explain. So we plotted it out. So this is a figure plotted out number of phantoms in existence. So you may consider this as the total numbers as available at a certain time. Plotted as a function of time. You can see before 80s, we have about 20 phantoms. That's pretty much it. But from 80s to 2000, the number increased exponentially to almost like 100. Now, if this plot continues, and then we are looking at maybe 1,000 or 2,000, who knows? So this growth actually follows, as I later realized, the growth of computer technology, which is not surprising anymore because computational phantoms have to do with the computer memory and the computer speed. So anyway, today I'd like to mention to those individuals who are interested in computer phantoms that my group, along with many, many other groups, we sometimes working together, some independently. We developed many of those anatomical modeling tools. And if you are interested, you can approach me or approach others to get hold of those computer tools so that you can begin using those methods. Now, as I mentioned earlier, what will be on the horizon? I think in terms of computational models, we're already looking at the DNA level of modeling. This slide I borrowed from Yan, from AIMBE. There is a group of people that are using giant DNA, which is a publicly available computational tool, and they're looking at modeling at the DNA level. So I think this will be a very interesting next step towards computational phantoms. So now I'm moving from the anatomical modeling to a CT dose and interventional radiology dose reporting software. Now, many people, 10 or 15 years ago, we became very interested in managing patient CT dose, particularly pediatric patients. And I am using these slides to highlight one particular article published in Lancet 2012. They look at a large number of young patients. They took CTs and look at, this is in UK, and a large number of hospitals. They published a number of studies on the dosimetry, and they find that there is a linkage between the exposed radiation dose and the risk later develop cancers. But I'm a physicist, so I would like to mention that in CT scans, there are certain radiation physics that we are interested in. For example, in CT, the level of X-ray energy, we're interested in photoelectric effect, but we're also interested in Compton scattering. So as you can see in this illustration, the pink rays are the X-rays that go into the area that physicians are interested, but because of the scattering, some other parts of the body may be exposed as well. So to simulate this process, we would have to consider both photoelectric effect and the Compton scattering. And 2 students in my group did that. We modeled the CT scanner, which includes the filter and the bow tie filter, and those data don't come around very easily. So we had a lot of students working on understanding the geometry of it. Now, of course, we did a Monte Carlo simulation. We actually considered the 27 phantoms. I think this is the largest study that including so many phantoms in the calculation. Our objective, the sponsor has to provide a commercial software, which we did, and then the Monte Carlo calculation, one behind it, consider all the patients' age, different gender, different size, and also CT parameters, as you can see. And all the data will be stored in a database, and the database is very comprehensive. As I mentioned earlier, we have 27 phantoms, so this is a huge database. But we're able to manage the data so a user won't have to run the Monte Carlo calculation yourself. You can just use the software to search for one of the phantoms that would match your needs. For example, in this interface, we are looking at an adult patient. You can change the scanning range interactively, and then you click your button in a few seconds. You are given a table and also a plot showing all the organ doses. You can choose to use the ICRP 103 or maybe an earlier version, ICRP 60, definition of the organ effective dose. And so it's very convenient. In fact, a lot of people discovered it was indeed very, very convenient on top of very accurate because we use so many second generation and the Monte Carlo simulation. So 2 years ago, almost 26 million users were recorded. And by the way, this software is based on the cloud computing. So everybody, can access the software very easily. Now, individual users pay a very small fee. Now, hospitals, you pay a little bit more fee, but hey, we got a large group of software programmers support the software. So this is a very robust software. It's been out there for many years. We also developed the similar software for interventional radiology. And this animation shows the interventional radiology. We actually have different angles you viewed when you consider how the patient is exposed. The third topic, which we will be looking at, a very, very important topic. If you are a researcher, I'm very sure that you are familiar with this topic. Some of you may even ask, why you use those phantoms? Those phantoms only represent certain size, certain shape. Can we develop a patient-specific phantom? So this topic is exactly for that purpose. How would we develop a patient-specific phantom? Well, most of you probably familiar with convolutional neural networks, but on this slide, I mentioned a particular slide, a particular neural network that's very easy to learn. Called UNet. It became available only a few years ago. And I asked a few of my students to learn this neural network that used to be only experts can handle. But students tell me this is pretty straightforward. Undergraduate student, master student. So several students become very good at it. Basically, this is very easy to learn. So we spend a lot of time to apply this neural network to some very good data. As you know, in the artificial intelligence today, we need to have very good medical data to train the neural network. So on this slide, we are looking at a particular set of long CT segmentation challenge data came out in 2017. And this is based on actually the Cancer Institute Imaging Archive. What they have is, those are the patients. The organs are already segmented by the experts. So we got hold of those publicly available data, and then we fed into the neural network that we have, and then we compare the data, how much the software has learned to segment. So on the top row here, you're looking at the original segmentation of the CT image. The CT image is segmented by very good physicians. Now the lower row of it is the image constructed from the software that we constructed. They basically learn from data. So from visual inspection, we feel pretty good because as a physicist, engineer, I can't tell much the difference. But quantitative data also tell you that the segmentation by the experts and the segmentation bound by the artificial softwares, they are very much similar. They are very good. They are very good. Of course, artificial intelligence software has a lot of other advantages. Now, of course, also we use the data from. There's also segmentation. On the top row, those are the what's called the gold standards. We would buy them K20, K40, K80. You know, right now there's many new ones. And we also had this Xeon 5. This is a CPU. We do need a CPU, so the GPU has to work with the CPU. So we do have a CPU, but we have a GPU. So GPU is a co-processor. Now, some people may think, well, I have a CPU code. Why don't I just turn it into a GPU? No, that won't now to work because GPU is based on a software environment called CUDA, and it's not compatible with the CPU, right? So you have to program into the CUDA environment, which is very, very difficult. Now, my students wrote a GPU-based Monte Carlo code from very basic level. So the CPU like this, GPU would be in parallel. They work together. We have photons, electrons, and protons, and others. But why medical physicists would be interested in a very fast Monte Carlo codes? Well, the medical physicists, they're interested in getting the patient CT and then finding out where the tumor is located, where the health tissues are located so they can protect those. And then they will do the dose calculation right here. Now, if they do it, if they take too long a time to do it, and then that would not be good. As I mentioned earlier, in the Chinese hospitals, every one of them would treat 300 patients or 400 patients. If you tell them the Monte Carlo codes take 6 hours, which some of the researchers would do, it's not possible. So it's very, very motivated to develop a Monte Carlo code is very fast. Now, we also treat a patient, and then we do what's called a QA. I would mention the QA a little bit later. QA is basically to verify the treatment planning results. We find a lot of errors let me show you some of the results next. This is what my students have done very recently. This is very fresh, has not been published. So to use the Monte Carlo, now of course you calculate those very fast, but you have to know the machine, the components, what they look like. They deal with electrons, photons, or they deal with protons. So this is an area called VirtualDose modeling. A lot of very good people in medical physics, they've done this, Charlie Ma, Lei Xin, and Steve Jiang, among others. Of course, Radhi Mohan is first at Memorial Sloan, and then WashU, and now is with Memorial Sloan Kettering Cancer Center. Now, he, of course, is the first to propose this method. But virtual source modeling has been around for a long time. But why we do source modeling when Monte Carlo is so slow? So I think today this is a renaissance of virtual source modeling. And here we are looking at a picture of how we done the modeling ourselves. So here's a comparing of results. So this is a step and shoot MRT, and this is a VMAT, and we published a lot of papers showing how we were to simulate all different kinds of machines. I forgot to mention the tomotherapy. This is also one of the very popular radiotherapy machines. And here are some papers in case we are interested in reading it. The top 3 are Ph.D. dissertations. The bottom 2 of them are applications to different machines. Now here's some result quite interesting. In 2014, we actually did a work with University of Wisconsin group. This is tomotherapy machine, and the GPU would calculate everything in 1 second. I apologize. And my colleagues in Wisconsin using Johnny 4, it took them a long time. Now, this may not be a fair comparison because our code is dedicated for therapy giant 4 is a general purpose Monte Carlo codes. But you can see the results are shockingly in agreement. They're very, very accurate. But GPU-based Monte Carlo can be very fast, can be almost real time. This is in 2014. And we went on to compare other cases in this situation. We look, this is different prostate. This is a prostate cancer treatment case. We compare also with yet another Monte Carlo code, EGS, NRC, and then here look at the difference. The difference is very small, and this is a 2D dose map. They are very similar, and then look at the dose volume histogram. But what's interesting is really the time. In the VMAT case, it took a little bit longer, but EGS took almost 1 day. This is, again, we published the work. You can take a look at the data. The software right now supports head and neck cancer, chest, abdominal tumor, and treatment planning. A few minutes is done. Now you can still give this result to an oncologist who would do this normally, like spending 1 hour, but out a couple of minutes, looking at data to see whether or not the student on scholarships, that means they are paid by the Chinese government. I think a student come from Pakistan, from Africa, and from India, from among some other countries, because they come here on full scholarship provided by the Chinese government. And I have finished teaching one student from Tanzania, Africa. He's a very good student. He got a PhD student from me. He had a master's back at home in Tanzania. So what I'm trying to say is, send me an email, and if you are interested in apply or interested in applying for the fellowships, so you can be supported by the government. If you are from other countries, yes, I think right now the scholarships target certain countries or regions.
Thank you. Regarding the recording of presentation, I believe everyone knows that we record all the presentations and make them available on the IUMP website within 24 hours, typically within few hours. So this presentation, including the discussion, will be made available on the IUMP website. The next question is, making Phantom is half the battle. How were you able to secure proprietary machine design to model your sources? He uses the SAS VirtualDose CT, and your machine library, he says, is enormous. How do you get the design needed to simulate sources?
Right. So this is a question that needs a lot of time to answer. If you are a researcher or a developer of a CT scanner, you would have to work with the about what geometries, what machines they use. I think there are several groups already published similar data, but because of confidentiality, we cannot release the information we have under the research agreement. So that, I don't have a good answer for that, but if you contact me in private, I can let you know what I understand, because we've done a lot of measurement, for example, around the CT machine. So we know the shape of the bow tie filter, for example, right? So, but other machines, if you have a different machine, GE's machine or Philips machine or Siemens, they are very similar. So you can make some measurements so that you can adjust the Monte Carlo model that you have for the CT scanner. Now, I think the question also asked about medical accelerator. Now, medical accelerator is very similar to the CT scanner in that you don't get exact information about what's inside of the medical accelerator. But again, the data is out there. You have to do some research to find those. Now, if you are just a user, my recommendation is to work with people like us, because I think my mission is to translate research into useful tools. Now, some of the tools may have to involve a fee. Now, I can tell you, those are not very expensive fees, considering the efforts that we put into it, considering the software people we have supporting the software. Software is very, very good to use. But, you know, if, for example, Archer, I had 3 PhD students working on it. It took more than 10 years. So my mission is not to make a lot of money. I think I'd be much happier if I see people like you guys are able to use the software to solve some clinical problems. So contact me in private if you're just a student, a user, or trying to get into the area of research.
Thank you, George. Next is, are any of the GPU-based Archer Monte Carlo tools available as open source?
No, right now it's not open source because as I mentioned, the GPU portion of it is very complicated. So you will need a lot of help to to get it going. Now, if I remember correctly, there are a few sporadic codes out there that you can get hold of if you are a software person or if you think you can do your own GPU-based. But my experience is a GPU-based can be used in the clinical setting. It will take a lot of effort. You can begin by looking at 3 dissertations in my slides. They're very good people. You can be even better, but what I'm trying to say is, why spend a lot of time trying to develop something that's not robust enough for the clinical application? And I believe me, we spend a lot of time to do that. Right. So I'm sorry I got interrupted a little bit.
Okay. So maybe I can continue because we have few minutes and I have reached not even halfway through the questions. So let us see as many as we can cover in the short time available. How do you calculate 3D TCM in VirtualDose CT?
Can you repeat the question? I'm not sure I captured it.
Requires a long answer. How do you calculate 3D TCM in VirtualDose CT?
Madam, can you ask you sharing your chat room so I can see which one you're looking at?
You can see yourself on the chat.
No, but I don't know which one you are looking at.
Yeah, this is at my 8:40 a.m. So this must be at your 8:40 p.m.
40, okay, now I see it. Okay, 40, okay. 40, okay. 40, okay, got it. Okay, how do you calculate 3D TCM in VirtualDose CT? Tube current modulation. So this is a terminology that I did not recognize earlier. 3D tube current modulation. This is a very good question. We did not calculate tube current modulation. The reason for that was we use MCMP to calculate, and as you know, MCMP took a very long time to calculate. For when you have a tube current modulation, every direction, every projection would require a new calculation. So we had to cheat. Basically, we calculate constant current, basically because we did not have Archer at that time. But today with Archer, we can calculate every projection in a few seconds. We actually can do the calculation again and then calculate TCM. So that's the answer.
Thank you. So do you have issues getting information from LINAC manufacturers like Varian with respect to?
As I mentioned earlier, all the manufacturers, they don't share the, the data. And there's some data out there showing structure information, material information, but it's very difficult to get those. Next question.
All right. So I think we are now reaching the time.
So next one, I can read it. What kind of parameters does the Archer return? So this is a very good question. So Archer, when we check the TPS, we come back with those volume histogram. we come back with two-dimensional dose maps, and then we will tell you whether or not this plan is acceptable. Now, acceptable plans typically will be 90%. That means gamma test showing our Monte Carlo result and a TPS data from Varian or other companies. They agree with each other 90%. Now, as many of you know, some of the commercial TPS, they are not based on Monte Carlo. So ours will be accurate. Ours will be actually able to tell you when the TPS fails in certain regions. As most of you know, when we have a heterogeneous area, air and bone, and the commercials TPS may not give you the best calculation result. So again, Archer will return those fundamental quantities. So you either verified or you are suggested cases where you may want to use a Monte Carlo-based calculation.
Thank you, George. Next is VirtualDose was validated on a number of CT scanners. How does the software transfer the dose tables to the scanners on the list to choose from, and how reliable are these conversions?
So this is a very similar question from the earlier individual. Yeah. So we moderated it. We try to find machine data as much as we have, but we also do what's called commissioning. So as you know, in commissioning, you adjust the parameters in the treatment system using measurement data. So we have very good measurement. We have very good system. So if you provide the measurement that you have on your machine, we would adjust our software so to match with your machine. All right, so let's look at the next one.
I think you can pick up one question more and then we are done.
Yeah. All right, one last question. Okay. All right. Well, some of them are thanking you for organizing the seminar, and
there are many thanks.
Stop right here. Yeah, I have one last slide to show if it's okay with you.
Okay.
So I'm on vacation, as mentioned by Madam, in China. Right now is a holiday. Today is the last day of the holiday. I spent one night at 5,500 meters above the seawater near Mount Everest, which is the tallest mountain. So this movie actually shows that I was on a hydrogen tank because I had reactions to the attitude of sickness, but I enjoyed it very much. And this is another picture of the Mount Everest. I wasn't on top of it. I was trying to show people that I was virtually on top of it. Was that a combination of a picture? And I visited Patala Palace, and I was very impressed. You know, I think Tibetans are very impressive people. They survive in a very difficult environment. They are very optimistic. They are very happy. And of course, I gain also appreciation for what we take for granted, which is the oxygen. And without it, you can't survive. This actually costs $100 a tank, the oxygen. I guess I should say that. I relocated to China in the beginning of the COVID-19, and I should have actually reconnected with a lot of my old friends and my colleagues, but I wasn't able to. But hopefully with this seminar, I be able to connect with some of the older friends, but of course, many of the new friends. So I would like to wish you the best wherever you are, and I also wish that in the not too long in the future, we can meet in person. And again, thank you all, and thank you, Madam, for organizing wonderful webinar series for so many years. You've done a great job for the medical physics community. Thank you very much.
Thank you, George, for this wonderful presentation and answering most of the questions. I apologize that the time is not enough for attending to all the questions. And we have the system of looking at the questions in the chat, which somehow get muddled by the many other messages. So we may not have the possibility to attend all the questions. So can you stop sharing, George, and I will share the information.